Good morning, all. Happy Monday. Happy start of the week. Uh, yeah, if you live in the Orlando area, you'll notice that it's gonna not very sunny out, and I bet you wanted to sleep in. I know I had trouble peeling myself off a pillow this morning, and I think it's just weather. It's kind of a fall weather in temperate region. Um, so are there any questions before I jump to the lecture? We're starting a new unit today, the ecology unit. Um, and are there any questions like about the lectures before or any logistics regarding the quizzes, exams, etc.? All right, if not, I'll get started. Couple of reminders. Quiz 9 is open and it's due on Wednesday, not on Friday, but the day after tomorrow. We're switching up our quiz due dates. So quiz, everything, all the material that is going to be covered on quiz 9 has already been taught. Okay, so it has the material covered in quiz 9 is about evolution. None of the material covered in this lecture or next lectures is going to be on quiz 9. Quiz 10 opens on March 25th, so technically after midnight that the quiz 9 is due, which is when quiz 9 will be due. And the quiz 10 similarly will be due on Wednesday, March 31st. And we have a participation assignment that is due today. So please check the modules section or quizzes section or your calendar, course calendar, to complete the participation assignment. Make sure you submit it before 11:59 p.m. today. All right, so new module. Today's lecture is, and possibly a bit of tomorrow's lecture, is going to be about populations and population ecology. So what influences populations, some important terms that are associated with the populations that are important to know, as well as some properties of populations. So first, a little bit of review. Let's review the organization of life, starting with an organism as the smallest unit, and kind of make distinctions between population, community, ecosystem, and biosphere. In a quiz that was due long time ago, I noticed there was some confusion what biosphere was. So an organism is a single individual. So this single acacia tree is an organism. So it's a unit of an individual that can function on its own. Okay. So population is a group of individuals, a group of organisms of the same species living in the same place at the same time. So an example, if we're sticking with acacia trees, then a population is going to be a group of acacia trees living at the same place at the same time. Okay, so if a population of acacia trees spanning over 20 years, it's not going to be technically a population because they're not located at the same time. Similarly, acacia trees that are, let's say, acacia trees that live in African savanna and acacia trees that live in, I don't know, Hawaii, they're not going to be the same population because they live in different places. And community is basically all populations of various species that occupy the same region. So if we're looking at African savanna, then a community would be all the populations of the acacia trees, the population of elephants, the population of lions, the population of the graminoid species that occupy the understory of the acacia wooded area. Uh, so community is the all populations of living things that occupy the same region at the same time. Now, ecosystem is basically community expanded to non-living things. So ecosystem is the living and non-living components of an area. So community is basically what was our community? So a population of acacia trees, a population of lions, a population of elephants, a population of graminoid species, and the ecosystem would be the community plus water that is found in the area, plus the soil, plus the other non-living components of the area, like rocks and stuff. Now, biosphere is basically ecosystem at the global scale. So the parts, biosphere is the parts of the planet and its atmosphere where life is possible. So biosphere is the largest unit in the organization of life. It's basically everything that occupies the planet Earth, including the atmosphere. Okay. Hopefully it was clear and it was supposed to be a review, but in case not, are there any questions about the distinctions between community, ecosystem, and population? Those can be hard ones. Okay, I'll have a question for you then. So let's consider the city of Orlando and its suburbs. So what would be, can you give me an example of the community within Orlando?
A community in Orlando could be like the population of multiple high schools in Orlando.
Okay. Multiple high school. Anything else? Good start. I would say you covered the population because your example included only people. Okay. So what? But community includes populations of various species that occupy the same region. So Joshua, can you try and expand your definition of community for Orlando area or Orange County?
So the people, as well as maybe trees and other organisms.
Yeah,
Like,
so people, trees, roaches, birds, alligators, what have you. Okay, great. Now, can anybody tell me an example of an ecosystem in Orlando? Let's say, oh, shut up. Ecosystem of Orlando. Can somebody describe an ecosystem in Orlando?
Could it be like the campus of UCF along with the rivers and lakes here?
Yeah, nice. So campus at UCF, we have people, we have squirrels, we have, so at first I'm going to describe a community. We have people, we have squirrels, we have roaches, we have, what else is there? Birds of various species. We have tortoises, we have snakes, and now that I've described community, plus we have ponds, we have asphalt, we have soil, and yeah, so ecosystem, when you're describing an ecosystem, think of describing populations of various species as well as non-living environments. So non-living environments in case of UCF campus would be ponds, maybe fountains. Uh, is there a stream? I don't think there's a stream there. Yeah, soil, asphalt, concrete, parking garages, buildings, and so on. Hopefully that was clear and gave you more confidence in describing, giving example of an ecosystem, community, and populations. So populations live in a habitat or a physical location where individuals live. So habitat, again, is a physical location where members of a population normally live. For instance, these palm trees here, they live in a desert, whereas the penguins, they live somewhere near the shore in, let's say, in Antarctica. Now, second important term associated with population is population density. And population density is a property of population that has to do with number of individuals living in a certain area. So it's number of individuals of a species per unit area or a unit volume of a habitat. So habitat is where the species live, and population density is number of individuals per unit area. So within habitat, there can be many individuals or a few individuals. If we focus on people, human populations, then let's say a population, the most densely populated country in the world is a country called Monaco. Does anybody know where it's located? France, you're in Europe around Italy. So Monaco, it's its own country, and it's not technically France. Okay, it's separate from France, and it borders with France and it borders with Italy. So in the nice, it's located in the Nice region, and it's very famous for its gambling attractions. And the Monaco is also the most densely populated country, and it has population density of 20,000 people per kilometer squared. And the least densely populated uh, country is Mongolia, where there are only 2 people per kilometer squared. And Mongolia is located in Asia. It borders with China, I believe, on the south, and with Russia. So uh, let's think about Monaco, where there are 20,000 people per kilometer square. And if all the people would go outside or from their homes and just stand outside, it would be probably the individual person would have only 50 squared meters of personal space. So 50 squared meters is not a lot. If you're wondering what is it in square feet, you would need to multiply it by 9.3 or 9.4. So I'm rounding. So not a lot. It's like, well, a good sized room, maybe. Um, but it's dense. Okay, there's a lot of people in Monaco. So population density varies among species. I just gave an example for humans, but it varies across species. So this example shows widely spaced population density. So in case of the palms, that are pretty widely spaced clumps. And there is a population in this figure that is very densely packed. For instance, population density of penguins tend to be um, well, low, or rather high. Population density is high because penguins like to stick together and hang out together. And when it's cold, they huddle to keep warm. So population ecologists estimate population size frequently because they're interested in the changes in population sizes over time. So ecologists study population size and density over time, and they use several methods to count population number. They use aerial photos, and aerial photos are pretty useful to get a snapshot of a population at one point in time. So for instance, aerial photos are widely used to estimate the population size of penguins, population size of trees, and various other species that don't move around too much and are kind of densely populated. Um, Also, the second method of estimating population size is basically sampling a small subset of the population per unit area, and then extrapolating that number to all of the area. So, sampling a small subset of a population is widely used for populations that do not move around too much. So, for plants, for instance, plants don't go anywhere. So, you kind of can select a sample area and then count the number of plants of one species, and then extrapolate that number to a larger area occupied by a particular species of plants. And finally, mark recapture method is used for species that move around a lot. For instance, if you want to estimate the population size of dolphins of a particular species in a particular habitat, or whales, how are you going to do that? I mean, it's pretty, aerial photos will not tell you much because you cannot really see very well through water. Sampling small subset is virtually useless for the species that move around a lot, because you can count the same individual twice or 3 times or 4 times because it can move to different area. But if you catch an individual, mark it, and release it back into the wild, and then go out sampling or go out counting individuals again and do the same thing. Basically, mark recapture method of estimating the population size deals with counting how many individuals that were marked previously are recaptured. Okay, so there's some formula, which I'm not going to discuss for this class, but there's a formula that kind of estimates the population size from the proportion of recaptured individuals that were caught before. All right, and are there any questions about population estimation?
Can you go over sampling small subset again, please?
Yeah, sure. So let's say you want to sample this species of palms. You don't, and these palms, let's say they grow in the Saharan desert, which is pretty huge. And you know that the palms are distributed across all of the Saharan desert. But you obviously don't want to go around the Sahara and kind of count all the palms. So you choose a sample plot. And your sample plot, let's say, would be I don't know, 100 meters by 100 meters. So pretty walkable. And you walk around and count the palm species. And you obtain a density, the population density of palms per, what did I say, 100 by 100 meters or 50 by 50 meters?
100 by 100.
100 by 100. So 100 times 100 would be 10,000 meters squared. So you walk around, you count the palms, and you figure out that there are 100 palms per 10,000 square meters. Then you multiply this population density by, well, first you divide 100 by 10,000, and it would be, oh God, 0.001 palms per meter squared. And then you multiply this number by the total area of the Saharan desert. And that's how you estimate the population size, by sampling a small subset of Saharan desert. And that's how you basically, you get population density per meter squared from a small sample plot, and then multiply this number by the total area of the Saharan desert. And that's how you calculate the total number of palms in the desert. Did that make more sense?
Yeah, it made sense. Thank you.
Okay. So Lauren asks, how do we calculate population density? We count the number of individuals per unit area. Okay, so in case of the palms and in the desert, we basically choose a fixed area, 100 by 100 meters, count the number of palms, let's say it will be 100. And then to get population density, you divide the total number of palms by the total area. So it would be 100 by 10,000. And that's going to be our population density. The units of population density are a number of individuals per unit area, okay? And Sekyun asks, can you go over aerial photos again? Yeah, so basically you fly a plane or hire somebody to fly a plane with really good camera on board, and you take photos from above. And you can use it to calculate the population sizes for trees or plants, or you can calculate the population sizes for the species of animals that do not move very much and are distinguishable from a plain view. So the example I gave, the penguin populations are frequently estimated, I should say, with aerial photos, because penguin populations at particular point in time, they tend to stick together and they tend to hang out together. And that's why it's kind of convenient to fly a plane over them, to take pictures, and then use some computer software to calculate individual penguins. Oh, like a drone, yeah, or a drone, not necessarily a plane or a drone. I'm not in the 21st century yet. Okay. Moving on. So, population size can grow, remain stable, or decrease. So to grow, a population adds more individuals than are lost. So when population is growing, that means that the birth rates exceed the death rates. And to remain stable, population adds the same number of individuals that are lost. And finally, if population size is shrinking, that means that the death rate, or the number of individuals that are dying, is higher than the number of individuals that are born. So I used birth rate and death rate, and let's define those terms and understand what they are. So a population's birth rate is the number of new individuals produced per individual in a defined time period. So birth rate is number of individuals that are born per individual within a population in a defined time period. So can anybody, from this definition, can anybody kind of deduce what are the units of measurement of the birth rate? Number of individuals that are added to a population per individual. Ava says individuals. Good try, but no. Not quite. So number of individuals per individual. What kind of units of measurements are those? Farouk says per population. Good try, but no. What are the units of measurement of birth rate? Offspring per year? No. Let's think about it. Like the birth rate is the number of new individuals produced per individual. Alexander is guessing offspring per year. Offspring per death, no and no. Birth density, Samir says not quite. Madeline says offspring per individual, yes, but what kind of units of measurements would those be? It's a fraction, it's unitless. Because if you visualize number of individuals in the numerator, and per individual. So units of measurements in the numerator would be individuals, and per means, you know, the fractional line, and individual would be in the denominator. So numerator is individuals, denominator is individual, and those two individuals kind of go away, leaving a fraction. So birth rate is a fraction. It's technically number of individuals per individual, but when you see it, it's going to be usually a fraction. Okay, it's unitless. Does it make sense why it's unitless?
Yes.
Great, thank you, Joshua. Joshua is alive. Great to hear. Great to get feedback from you guys, or participation. So if you get like birth rate of 0.01 and the population size of 100 individuals, how many individuals are born within a population per year? 1, Matthew, excellent. So Christine says it doesn't make sense why it's a fraction, why the population birth rate is a fraction. So, okay, imagine the fraction, okay? And in the numerator, the units in the numerator are individuals. The units in the denominator are individuals as well. And if it were a number, you would just cross out the number, the same number in the numerator and denominator, and would be left with 1. The same thing kind of can be done with the units. So individual in the numerator would be, and the individuals in the denominator would kind of cross out, and we would be left with technically 1, or unitless measurement. All right. So the factors that are affecting birth rates are, well, or the factors that are affecting additions to the populations are birth rate. And the birth rate is affected by the number of reproductive episodes per lifetime. The more reproductive episodes, the higher is the higher number of births there are, and that should be like common sense. The births are also affected by the number of offspring per reproductive episodes. The higher number of offspring per reproductive episode, the higher are the births. And the age at first reproduction also affects the births. So the younger the age of first reproduction, the higher births will be in the population. And finally, the population age structure affects the births, and I will go into population age structure in detail a couple of slides from now. And the second part that affects the addition into the population is migration into the population. And it's affected by the availability of dispersal mechanism, meaning some sort of mechanisms that would, well, literally disperse the individuals within a population. And availability of the suitable habitats. If there is no suitable habitats, the immigration will not take place. Or the individuals that would have migrated into the population, they would die because there would be no suitable habitat to support them. Now, deaths and immigration decrease population size. The death rate of a population is the number of deaths per unit of time. Scaled by the population size. So the death rate can be expressed as both number of individuals per that died per unit of time, or number of individuals per individual that have died. And if it's expressed as a fraction, then it's pretty easy to determine the population growth rate, because if your birth rate and death rate are both expressed as a fraction, where common denominator would be the population per individual, maybe number of individuals in the population, then to calculate the overall rate of population change, you would subtract birth rate. You would subtract death rate from birth rate. So birth rate minus death rate would be the overall rate of change within the population. So deaths and immigration are affected by multiple things. The death rate is affected by accidents. Whatever accidents happen, they kind of take away from the population. The genetic and or infectious diseases, they affect the death rates. Predation affects the death rates, as well as nutrient availability affects the death rate. So nutrient availability is a big deal for plants. If there is not enough nitrogen or phosphorus within the soil, you'll see mortality, increased mortality in the plants, because they cannot produce enough sugar through photosynthesis to support their growth and even existence. And another source of loss of individuals from a population is through emigration. And to what affects the rate of emigration is the availability of a dispersal mechanism, meaning some mechanism that the individuals who decided to emigrate from a population would use to get away from the population, from the old population and into the new population. So the age structure, I mentioned that the age structure can be used to, the age structure affects the birth rates. So a population with many young individuals reproducing individuals is likely to have a high birth rate and therefore grow. So in this figure, there are two figures here. One showing the age structure of the white oaks population, and another one showing the age structure of the cottonwood population. So the white oaks can be very, very, very old. They can be over 300 years old, whereas the cottonwood population is much more short-lived. So the maximum age that cottonwood on average get to is 70 years old. Now, a bit of thing, a fact that is going to be helpful in interpreting age structure is that younger individuals, they're going to reproduce more efficiently than older individuals. So let's take a look at the graphs more closely and interpret them. So on x-axis of the graphs are the age of individuals. And on the y-axis are the percentage of trees in a particular age bin. So within this white oak population, there are going to be about 65% of all of the individuals are going to be the age of 50. 22% of individuals approximately are going to be of the age of 100, about 10% going to be of the age of 150, and so on. So in the white oak population, a lot of the individuals, 65% of individuals are going to be young. But as the time moves on, as the time goes, this age structure is going to change. Like in 50 years, all of these guys, or most, depends on the death rate, but let's say death rate is going to be negligible, and all of these guys are going to move into this bin right here. All of these guys are going to be moved in this bin right here. All of these guys are going to be moved over here, and so on. If we look at these population age structure 50 years from now, it's going to be looking a bit different. But what's important to understand here, if there are a lot of young individuals within a population, the population is projected to increase because all of these young individuals are going to reproduce more efficiently. All of these guys are going to produce lots of offspring. So 50 years from now, the shape of this curve may even be preserved because 50 years from now, these guys are going to be replenished by the individuals that were formerly located in this bin. So it's kind of a long-winded explanation, but does it make sense why the population that has a lot of the young individuals is projected to increase? Monica says yes. Okay, is anybody confused about why the populations with many young individuals is projected to increase? Christine says no. Great, yay. Now let's take a look at this graph here, which shows the age structure of the cottonwood. The x and y axis are the same. Basically, x-axis is the age bin of individuals within the population, and the y-axis is percentage of trees that fall into this age bin. So within the white oak, I'm sorry, not white oak, within the cottonwood population that lives to 70 years, most individuals are between 40 and 50 years old. So the individuals that are 40 years old, there's about 42% of them, and about 45% of individuals are 50 years old. So over 80%, or was it 80? Yeah, over 80 something percent are kind of middle aged. Now, there's not a lot of young individuals within the population here. So after 50 years, this guy, well, after 50 years, all of them will be dead. But after 10 years, these guys will move here, these guys will move here, and these guys will move here, these guys will move here. Now, more individual, like most efficient reproductive rate is found among the younger individuals. So these guys will not produce many individuals. These guys will not produce many individuals. And these guys are kind of getting old and not produce any individuals like as a background, at a background rate. So this population, the population of the cottonwood, because it doesn't have very high number of individuals of younger age at which they reproduce most efficiently, the population of cottonwood is projected to decline, like, because there is lots of old individuals compared within a population, and old individuals are going to die soon and not reproduce very well, whereas younger number of individuals is there's not enough young individuals within the population to sustain a stable population size or increasing population size. So population size will decline because of low proportion of the young individuals here. And a couple of slides from now, we'll also go over, apply this principle to human population, and it might make more sense, like it might click better when human population example is given. So another important property and another important thing that we're going to discuss is the life tables. The life tables are associated with populations, and basically they show that the probability of surviving of individuals within a population to any given age. So in this example, researchers determine how many individual penguins survive to a given age. And these life tables are very frequently used by life insurance companies, and they use basically human life tables to calculate premiums for clients of different ages. So first, let's look at the table. And this table describes the survival rates for this penguin population. So at age 0, let's say we have 1,000 individuals that were born in the population. At age 1, and we imagine we observe this population, this cohort of 1,000 penguins over time. And we observe this cohort of penguins for 16 years. Now, we started with 1,000 individuals. We come back after 1 year and count the former babies that were born in a particular year. And we see that only 324 individuals have survived compared to the original 1,000. We come back the next year and count only 278 individuals. After 3 years, 242 individuals remain, and so on. We can express all of these numbers as fractions if we divide all of the numbers right here by 1,000 or by the original number of penguins of age 0 that we started with. We will get the probability of survival, okay? And it will be a number between 0 and 1. And these probability of survival is what is used by the life insurance companies. So let's take a look at the graph here. The graph here, basically, it plots this table where x-axis is the age and the y-axis is the number of survival. The y-axis kind of looks funky here because it's on a log scale, and it's on the log scale to kind of be more user-friendly, more visually attractive, and explain what's going on. So we started with 1,000 individuals, and over time, after first year, we are left with 324 individuals. So technically, this is 30% survival rate by the age of 1. Now, after 5 years, we have 193 individuals. So it's roughly 20% survival, or more precisely 19.3% survival rate to the age of 5. After 10 years, we have 110 individuals that survived. And if we divide it by 1,000 and multiplied by 100, we will get percent survival rate. And what it will be is basically there's 11% chance that an individual penguin will survive to 10 years, to be 10 years old. Now, let's merge the two principles. Let's think about the following a little. Imagine a life insurance company that insures penguins, and let's say a baby penguin is born and goes into a life insurance company and says, I want to buy an insurance plan, a life insurance plan, because I don't want my parents to my parents will depend on me when they get old, and I want to support them if I'm dead. The life insurance company evaluates the survival table for the penguins, and it sees that, well, the penguin has 30% survival chance to the age of 1. What do you think? Will the insurance premium be high or low for the baby penguin who wants to insure its life? High, very nice, very nice. So insurance company basically is taking on a high risk. 30% survival is pretty low. I mean, for humans, it's virtually 100% survival rate to the year of 1. And with humans, it's pretty much high survival rate, period, because of the modern medicine. But for penguin, 30% survival rate is pretty darn low. And in case the penguin dies by the age of 1, which is pretty short term, the insurance company would have to pay out a lump sum to the penguin parents. Yeah, same works with humans. And personally, I think it's an ethical practice of life insurance because insurance companies are for profit. I would be more okay with it if it were non-profit, but making money off of people's deaths, it just sounds not good. So there's that. Are there any questions about life tables and how we get from the number of individuals to percent survival by a certain age? Okay, Lauren asks, can you describe how to interpret the graph one more time, please? Sure thing. So on x-axis, we have years since birth. And on y-axis, we have number of survivors out of the 1,000. So on y-axis, there is technically number of individuals. Now, how did we get 30% survival? So after 1 year, 324 individuals remain out of the original 1,000. So to get the rate, we divide 324 by 1,000 and multiply by 100 to transform the fractional units to percentages. So we have 32.4% of individuals that have survived to the age of 1. Okay, now let's look at the 5 years. The graph says 20% survival, but let's calculate a more precise one. So here's 5 years, and we have 193 individuals out of the original 1,000 that survived to be 5 years old. And to get the percentages, we divide 193 by 1,000 and multiply by 100 to get the percentages. So it's going to be 19.3% of individuals out of the original 1,000 that survived to be 5 years old. Lauren, what's that more helpful? Great. Moving on. Survivorship curves follow some predictable patterns. And there are basically 3 patterns for survivorships across 3 species. Having said that, a lot of patterns are kind of a mix between the two. But most of the individuals follow either type 1 survivorship curve, type 2 survivorship curve, or type 3 survivorship curve. So the x and y axis in this graph are the same as they were in the previous graph. So x-axis is age in years, and the y-axis is the number of survivors. And the 3 curves are basically theoretical. There's no hard numbers attached to them, so don't interpret it literally. It just shows the shape of the curve if you were to explore various populations and create a plot of create a plot of survival tables for those species or for that population. So in type 1 survivorship curve, species invest energy for caring for their young, and most individuals survive to reproduce. So let's take a look at it again. So as the age progresses, basically virtually all of the individuals survive, and then they start dying of old age and diseases once they get older. In type 2 curve, species have an approximately equal chance of dying at any age. So we see that survivorship kind of declines uniformly as an individual age or as a population ages, as a cohort from a population ages. And finally, type 3 survivorship curve. It's very characteristic for species that invest little energy raising their young. So few individuals survive to reproduce. So a species like, I don't know, fruit flies produce lots of offspring, but they don't care if the offspring live or die. They don't tend to them much. So basically, and as a result, the survival rate for the very young individuals is very, very low. So we see a sharp drop in the number of survivors at the young age. And then the mortality rates or the survivorships becomes uniform, and it kind of follows the asymptotic level to the old age. So very few individuals survive to be a ripe age of, I don't know, 3 days for fruit flies. Okay, so I have a question for you guys. What kind of survivorship curve, type 1, type 2, or type 3, do you think humans have, people have? Type 1. Woo, that was clear and that's great. And in this example with the penguins, what does this survivorship curve look like? Which type? Okay, I see 2, I see 3. So it's actually in between the type 2 and type 3, because there is a sharp drop in survival rate for the young, but then it's kind of, the mortality is uniform. So technically, most of the bird species are type 2. So for penguins, I would say it's in between type 2 and type 3, because the mortality of the young is not as high as mortality, for instance, fruit fly. That was a difficult question. As I said in the very beginning, when I was describing this slide, a lot of species fall in between type 2 and type 3. A lot of bird species, I mean, fall in between type 2 and type 3 curve. All right, so we see that the survival rate can be very, very different across species, but the populations, we kind of see that populations of fruit flies are stable, despite that a lot of individuals die when they're very young. The population size does not necessarily decrease. Somehow we see a lot of fruit flies if we leave fruits out. And the same with birds, despite that, a lot of individuals die when they're very young. We see that birds' populations do not go extinct unless you destroy their habitat. So in a stable population, birth rate has to complement the death rate. So reproductive strategies also fall into this pattern. So there are two types of reproductive strategies: opportunistic and equilibrium. So in the individuals with type 1 curve and basically type 2 curve, the reproductive strategy is equilibrium strategy, and it's in type 3 curve in the species that have type 3 reproductive survivorship curve. The reproductive strategy is so-called opportunistic. So what is the difference between the two? Species with opportunistic life histories produce many offspring. So they reproduce whenever there is an opportunity, and they produce a lot of offspring, but they don't take care of it. So examples of species that have opportunistic life histories, it's basically weeds, insects, and many other species with type 3 survivorship curve. And their strategy is to basically reproduce a large quantity of offspring, and not take care of them. Just whatever survives. And but because they produce a lot of offspring, there's still many individuals that survive. All right, it's 10:20, so are there any last minute questions? And if not, I'm just gonna pick it up on Wednesday. Sarah asks, is there any extra credit for this class? Yes, there's going to be extra credit points for this class, and they're going to be available during the week after finals. So after you come back from the spring break, you'll able to evaluate your grade, where it's headed, and that's when some extra credit opportunities will be available for you to take. Any other questions? All right, well, I'll see. Yes, Christine, our final is before the spring break. It's going to be on Friday before the spring break. So you're gonna take your exam and just take a rest during spring break and not worry about the exam. All right, thank